Download this code from codegive.com, link in the description below. OK, let's dive deep into JavaScript core internals, focusing on the critical distinction between boxed and unboxed values. This is a fundamental concept that impacts performance, memory usage, and overall understanding of how JavaScript core executes code. Understanding the core concepts, values, types, and representation. At the heart of any JavaScript engine, including JavaScript core, lies the concept of a value. A value represents a piece of data that JavaScript can manipulate: numbers, strings, booleans, objects, and more. The engine needs to efficiently store and operate on these values. This is where the boxed versus unboxed representation comes into play. JavaScript values are dynamic. One of JavaScript's core features is its dynamic typing. You don't explicitly declare the type of a variable, it's determined at runtime based on the value assigned to it. This flexibility comes at a cost: the engine must track the type of each value dynamically. Value representation. How does JavaScript core actually store these values in memory? It uses a clever system that involves both direct representation, unboxed, and indirect representation, boxed. Boxed versus unboxed, the key difference. Unboxed values, direct representation for certain simple data types. JavaScript core attempts to store the value directly within the memory allocated to represent a JavaScript value. This is the unboxed representation. The most common types that can be unboxed are small integers, often called SMIs or small integers, and sometimes booleans. Unboxing avoids extra memory allocation and indirection, leading to performance benefits. Boxed values, indirect representation for more complex types or values that don't fit within the directly representable range. JavaScript core uses a pointer, a memory address, to a separate memory location where the actual value is stored. This is the boxed representation. Objects, arrays, strings, floating point numbers, and large integers are typically boxed. The pointer points to a structure in memory that contains the value and, often, additional metadata, like type information, reference counts for garbage collection, etc. Why use both boxed and unboxed representations? The choice of boxed versus unboxed is driven by a trade-off between performance and flexibility. Performance. Unboxed values are faster to access and manipulate. The engine doesn't need to dereference a pointer to get the actual value. Operations on unboxed values can be much more efficient. Memory efficiency. Unboxed values consume less memory overall because they don't require separate memory allocation for the value and a pointer to it. Flexibility. Boxed values allow JavaScript core to represent a wider range of data types and values, including complex objects and dynamically sized data structures. Dynamic typing. Boxed values are critical for handling dynamic typing. The extra metadata stored along with the value allows the engine to determine the type of the value at runtime. JavaScript core's implementation details. Illustrative. The exact implementation of boxed versus unboxed is highly dependent on the specific JavaScript core version. However, here's a simplified, illustrative overview of the underlying mechanisms. 1. The JS value type. JavaScript core typically defines a JS value type, or something similar, that represents a JavaScript value. This type is often a 64-bit, or 32-bit on older architectures, word. The bits of this word are carefully partitioned to encode both the value itself, if unboxed, and / or type information. 2. Tagging. A common technique is called tagging. Certain bits within the JS value are used as tags to indicate the type of the value. For example, Asterisk if the tag bits have a specific pattern, example the least significant bit is set, the JS value might directly represent an SMI, small integer. Asterisk if the tag bits have a different pattern, the JS value might be a pointer to a heap allocated object, i.e., a boxed value. 3 small integers, SMIs are typically represented by shifting the integer value to the left by 1 bit and setting the least significant bit to 1. This allows JavaScript core to quickly distinguish SMIs from pointers. For heap allocation * boxed values are stored in the JavaScript core heap. When a new object, array, or string is created, memory is allocated on the heap to store the data. The JS value then holds a pointer to this memory location. Code example, illustrative, not directly executable. This example illustrates the concept of boxed versus unboxed. The actual C++ code within JavaScript core is far more complex and optimized. It is not executable in its current form. It's meant to demonstrate the conceptual representation. Explanation of the illustrative code * 1 JS value union * the JS value union is used to demonstrate the core concept. It can either hold a raw 64-bit value, representing the SMI or a pointer, or be interpreted as a structure containing the value and a tag. This union allows the same memory location to be interpreted in different ways based on the type of the value. 2 is SMI function * this function checks the tag bit to determine if the JS value represents a SMI. 3 get SMI value function * this function extracts the integer value from the JS value by shifting the bits to the right. 4 create SMI function * this function creates a new SMI value by shifting the integer value to the left and setting the tag bit. 5 create object function * this function creates a new JavaScript object and stores a pointer to it in the JS value. In a real implementation, you'd need to use a tagging mechanism to indicate that the JS value is a pointer to an object. Important considerations and optimizations * type inference * JavaScript core employs sophisticated type inference techniques to try to determine the types of values at compile time. If it can prove that a variable will always hold a SMI, it can optimize operations on that variable to use unboxed arithmetic directly. Inline caches ICS inline caches are a crucial optimization technique. When a function is called repeatedly with the same types of arguments, JavaScript core creates a small cache that stores the type information and the optimized code for those types. This avoids the need to perform type checks on every function call. Garbage collection * boxed values are managed by JavaScript core's garbage collector. When an object is no longer reachable, the garbage collector reclaims the memory it occupies. Reference counting and mark and sweep are common garbage collection techniques used in JavaScript engines. String representation * strings are often handled differently from other objects. JavaScript core might use specialized string representations, such as rope-like structures or flat arrays of characters, to optimize string operations. Small strings might even be stored directly within the JS value, similar to SMIs. Floating point numbers floating point numbers are generally boxed. JavaScript core might use techniques like double tagging to directly represent some floating point values in a JS value when possible. Impact on performance Understanding boxed versus unboxed values is essential for writing performant JavaScript code. Favor integer arithmetic operations on integers, within the SMI range, are generally much faster than operations on floating point numbers or boxed values. Try to use integers whenever possible. Avoid type conversions unnecessary type conversions can force the engine to box and unbox values, leading to performance overhead. Try to ensure that variables have consistent types throughout your code. Use profiling tools. JavaScript Core provides profiling tools, like the Instruments app on Mac OS, that can help you identify performance bottlenecks in your code. These tools can show you where boxing and unboxing are occurring and help you optimize your code. Understand V8 and SpiderMonkey. The concepts of boxed vs unboxed exist across different JavaScript engine implementations such as Google Chrome's V8 and Mozilla Firefox's SpiderMonkey. It's useful to research these engines to understand their specific implementation for greater breadth. How to detect boxing, indirectly. You can't directly see if a value is boxed or unboxed. The details are internal to JavaScript core. However, you can infer it from performance characteristics. Measure execution time. If you perform the same operation repeatedly with different types of values, you might see a performance difference that suggests boxing is occurring. Use profiling tools. Profiling tools can sometimes expose the overhead associated with boxing and unboxing, even if they don't directly show you the internal representation of values. Monitor memory usage. Frequent boxing and unboxing can lead to increased memory allocation and garbage collection activity. Example scenario: optimizing a loop. In this example, if the ARR array contains elements of mixed types, example integers and floating point numbers, the SumArray function might experience more boxing and unboxing. If ARR contains only integers within the SME range, the SumArray optimized function might be faster due to the engine's ability to perform unboxed arithmetic. In summary, the boxed versus unboxed value representation is a fundamental concept in JavaScript core and other JavaScript engines. Understanding this concept can help you write more performant and memory-efficient JavaScript code. By favoring integers, avoiding unnecessary type conversions, and using profiling tools, you can minimize the overhead associated with boxing and unboxing and improve the overall performance of your applications. Keep in mind that the specific implementation details are complex and subject to change, but the core principles remain the same. Remember to benchmark and profile your code to confirm the impact of your optimizations. Good luck.